Now let's focus on kernel-based processing. Again, like I mentioned earlier, kernel-based processing is in some textbooks this process is also known as a linear filtering, two-dimensional linear filtering process, and is also called as a special filtering, meaning that in some textbook as well they use the word special filtering. Okay, when you see the word special filtering, actually it's referred to kernel based processing. Okay, before I discuss these 3 points, okay, again, like I said in the earlier discussion, when we talk about the kernel based processing, is actually involve what we call as a convolution. Okay, convolution process, or in other words, since we dealing with image processing, where image is a two-dimensional signal, kernel based processing is about what we call as a two-dimensional convolution process. Okay, to understand more about kernel based processing, you need to know what actually call two-dimensional convolution process is all about. Okay, now let's go through and recap back what is a convolution process that you have exposed earlier in biomedical signal processing or digital signal processing course. Okay, let's discuss about the convolution, starting from the one-dimensional convolution process. Okay, I just draw back this one, and I also would like to recap back. I think I obtained this slide from biomedical signal processing course. Of course, I hope I think it has been updated. Okay, this one has been updated by your lectures, but of course convolution is one of the important operation in one-dimensional signals. So this is how the convolution work. Okay, even if you don't know how to interpret this equation, okay, this is how we represent the convolution. Okay, in general, xn there is your input, and then this is your system functions. You convolve with your input to obtain your output. So that is the operation of the convolution operation. Okay, the star there represent the convolutions process or convolution operation. And then if you okay, I just copy this one and draw back in this whiteboard. Okay, the same equations there, and I try to draw back the block diagram. Then you can see that this is how actually the convolutions, if you represent it in graphical forms there, in order for you to obtain the y ends there, you need to convolve between your input signal xn and your system function hn. Okay, and then this one here, this part over here, try to relate with this one. Now this is actually called as a two-dimensional convolution. So you can see that the process and the form there is very similar. If you see this one, it's similar with this one. Okay, the difference is just a notation. Okay, now we are using f there to represent our input image. So that's why we have xy, where that is represent a two-dimensional signal. Right now we are processing a two-dimensional signal with this image. Okay, because this is at the input side, so that's why we call as input image. And in image processing, we always use the word the f to represent the input image, and then to obtain the output image, g. Okay, g is always become the output image. Then you need to do a convolution between your input image and the w over there, where the w here is similar to your hn in one-dimensional signal. Okay, it's a system function. Okay, it's a, in other words, it's also known as a filter. Okay, this one is the one that the w there, sorry, okay, the w here, okay, there are many names for this w. Okay, some call it as a kernel. In image processing, they call as a kernel. Instead of system function, they call as a kernel. And it also known as a mask. or filter. You can also call as a window. Okay, there's a many name for that one. Okay, you can use a kernel, you can call it as a kernel, you can call as mask, you can call as a filter, and most of the time I always use I always call it as a window, because that's why we use the notation W there represent the windows. And then again, like I said, why the kernel based neighborhood processing is about convolution, because of this thing. Okay, because it's involved kernel. The W there is a kernel, so that's why they call it a kernel based neighborhood processing, because you are dealing with the kernel, and anything you are dealing with, if you are dealing with kernel and you do some operation with the input image, then you involve a convolution. So that's why when you talk about the kernel based processing, it's about two-dimensional convolution between the input image and the kernels. Okay, and then of course this kernel, if you go back to these examples, okay, this slide there, okay, one-dimensional convolution, if you see there, in order for you, okay, this is some example, let's say this is the input signal, and then you want to do the convolution with this Hn, and then after this is how you do the convolution. You may try to to revise back what have you studied before in your biomedical signal processing, how to do the convolution in one-dimensional. And what the things that I will like to highlight here, this one, okay, Hn here have some value. This value is also known as your filter coefficient. Okay, so if, okay, just want to relate this one with our discussion in this whiteboard here. So Hn here have their own value, which is known as the filter coefficient. Okay, in that example you have the Hn equal to 1.111. Okay, this is actually the filter coefficient. Okay, I just write the coefficient there. So similar to this W in two-dimensional signal, this W or this filter here should have their own filter coefficient. Okay, it's not just represent something, but we call it as a kernel, because this thing is a set of consists of set of numbers, and that numbers is known as a filter coefficient. Okay, so now let's go back to this slide over here, because everything what I talked before is actually summarized or explaining this 1, 2, 3 point. Okay, 1 and 2 point over here. Okay, the first this point here, it said that, okay, for kernel based processing, okay, the neighbor pixel are weak with a matrix called kernel. Okay, neighbor pixel are weak with matrix and in a matrix called kernel. So this is when it mentioned kernel here, also known as a filter, mask, template, or window. So this point over here, just to explain to you, actually this is referred to your W there. Okay, WXY. Okay, meaning that in order for you to apply the kernel based processing, you need some window or filter or kernel that is represented by this WXY. Okay, and the value of filter are known as coefficient rather than pixel, meaning that this WXY, like I said before, the value is consists of some value, and the value of this point over here, this matrix here, is not known as a pixel. Okay, rather we call it a pixel. It's more suitable to call as a coefficient or filter coefficient. That is what I have discussed earlier in this slide. Okay, when we talk about the kernel, actually is a matrix. If you talk about, because now if you talk about one-dimensional signal, it's just one-dimensional matrix like this one. But if you talk about two-dimensional signal and you are applying the convolution, because this one is two-dimensional, you know, two-dimensional input image like this one, and your kernel over here should also, or the filter over there, W there, should also consist of two-dimensional signal or two-dimensional matrix like this, and inside this point is known as a filter coefficient. Okay, I just give some numbers there. This number in W, okay, if this is your W, the element inside this matrix is not known as a pixel. Okay, rather you call it as a pixel, is better or suitable for you to call it as a filter coefficient. Okay, while the input image, of course, anything there is pixels. So that is explaining the second, or the, I think the third point there in this slide. Okay, so I hope you all understand about that statement. Now I would like to discuss the last statement there. As each point, okay, as each point xy, the response of the filter is calculated by a sum of product. Okay, sum of product here is also known your SOP. I think you also learn this one in digital electronic digit. What is sum of product and product of sum and so on. So now it's a sum of product of the filter coefficient or the kernel. Actually, this is explaining how you compute the two-dimensional convolution. Okay, when you apply the sum of product, it's actually a convolutional process. Now it's not just convolutional process, it's just it is actually a two-dimensional convolution process. Okay, so I will try to explain or prove this one in the next slide. Okay, now let's go to the example, then we try to relate back with this statement. Okay, this is example how you compute a two-dimensional convolution in image. Okay, again, this is input image F, and then this is your filter or kernel. I call it as a window, is better because W there. And then this is the one, this one is the filter coefficient, like that have been discussed in the previous slide. Okay, that's why they explain each kernel should have their filter coefficient, and instead of you calling this one as a pixel, okay, it's more suitable to you for you to call this the point inside this matrix as filter coefficient. Okay, it's not similar to the input image, because input image, this one is a pixels. So that's just this one is just try to differentiate between the input and the filter, because the filter, the element inside the matrix is the filter coefficient, but if you talk about the image, the element inside the matrix is the pixels. Okay, just different, the difference is that. Okay, to apply the convolution, this is how we do the convolution to obtain our G over here, output image G, this one. Okay, G x y, which is equal to our f x y convolve with our w x y. To obtain that, okay, you must process one by one, meaning that you must multiply. Okay, you, for example, if you want to find the pixel S7 over here, then you must do the convolution. When you do convolution, is actually you are multiplying this W1. You must put this window, okay, this window, I just call this window, is better, window, and then you put in this area. Everything overlap between this point and this point, you are multiply together. That's why if you, this one overlap with this one, you multiply together, and then you plus this one multiply with this one, plus this one multiply with this one. So this is how it's work, okay, to obtain the S7 over there. So that is the if you want, that is the first step if you want to find only this particular point of S7s there. So when you are applying that operation, this is product, this is product, and this is product. Everything here is a product. Okay, product, because you are do a multiplication between W1 R1, W2 R2. Once you apply all these things, okay, once you get all the product, you are summing together, you are sum up together, this one plus this one plus this one plus this one. So by having that operation, that's why you call in the previous slide there, okay, it's mentioned here is a sum of product, because you are doing this one. Okay, sum of product, because you are multiplying together. After that you are sum up together, so it's called as a sum of product. Okay, so that's why that is where or that is represent, or that is can be interpreted as a sum of product, but actually that operation is a two-dimensional convolution. Okay, that is only for if you want to get this one for this particular point. Then you may continue with another point to obtain S8 there. Then you must slide this window into this area. Okay, you must slide this window into this area. Anything overlap, you are continuing doing the same things. You are multiplying to get the product, and you sum up together to get the S8. Then after that you may continue to the next process where you want to get the S12. So of course, if you want to get the S12, you must overlap this window with this region. Okay, and then if you want to get your if you want to get your S13, then you must overlap this window with this window. Okay, this one. Okay, you may continue that one. Okay, this one is for the small or the simple operation or simple examples there. Okay, if you talk about the practical image, which is very big, like in the next slide, which is this one, then if you have having a same kernel where the size is 3 times 3, okay, then you may start from this point. Okay, then you must slide your windows in that direction until you arrive at this point. You must stop at this point in order for you to obtain your two-dimensional convolution operation. Okay, and then each point there you must process. So the question is, what happened to the border there? Okay, in our examples, okay, in our application in this syllabus, okay, what you can do, you just, okay, you just can put 0 there, 0 0 0 0, because most of the time any pixel that's at the borders there, at the border of the output there, is not processed, because our window is only fit into that one. Okay, if you talk about 3 times 3, okay, the window size is 3 times 3. Okay, you must start at pixel or the coordinate 1 1 over here. Okay, coordinate 1 1. Okay, if this is 0 1 2 3, this is 0 1 2 3, then you must start coordinate 1 1, you finish at coordinate 2 2, and the pixel at the borders there, you just put it at 0. Okay, if you talk about 3 times 3. Okay, later we'll discuss about the borders, about how to manage the border. Okay, but now we just focus on this operation. Okay, this is what we call as a two-dimensional convolution. Okay, how you compute between you do convolution between the input image and your kernels, and this is actually related to what we have discussed earlier. This is why we call it a kernel-based processing, because of you are doing a two-dimensional convolution. So if you talk about the convolution, of course you need a window or filter or kernel to convolve with your input image. So that's why instead of calling a two-dimensional convolution, in this chapter we call as a kernel-based processing, because it involves kernels there. Okay, that is the difference between kernel-based and non-kernel. Later we can see in non-kernel we don't have window, or we don't have a kernel there to proceed the image enhancement operation in neighborhood processing, under the neighborhood processing.